our week 2 with awful weather. Can't believe this many even showed up. I'm so happy. I'm shocked. How long does the homework take? My question is, raise your hand if it took less than 45 minutes. Oh, okay. Takes care of that. Wow. Where are we? So we're right here in week 2. Again, we'll have some boring stuff today. We're going to review the percentile, the quartile. We're going to talk about, again, the interquartile range, the regular range, but most of today's lecture is about this empirical rule. This is a key to understanding probability or statistics overall. This is kind of like one of the major building blocks right here. So this is where we're going to spend most of our lecture. And then next week's week 3, and then the week after that's our first big quiz, 10% of your grade. So it'll be on Tuesday of week 4, January 30th. Now, we left last week, my fault, that I completely forgot we had an in-class assignment. So we have to make up the in-class assignment we missed, because the other class did. So my question is this something you want to do? Don't forget, this is based on something I lectured on last week. And it's not hard, but you're going to have to search and figure out, okay, what is it that, how did we do this last week? But we can either do it at the beginning of class or we can do it at the end of class. And how it's going to be done is I put the problem up there, everybody works on their own piece of paper for a few minutes, and you get up and start comparing with other people in other rows. You can compare in your own row this first couple weeks, but after that it's all about getting to different parts of the room to compare, and it's about helping the other person figure out why your answers are different. You want to do it at the beginning of class or end of class? Raise your hand for beginning of class, and raise your hand for end of class. That's about even, you guys, and a whole bunch of people didn't vote. So some bunch of you don't even care. I think. Here's the problem with doing it at the beginning of class is that what if someone's taking extra long, we're all waiting. That's the only thing I'm worried about. I don't want to put a lot of pressure on someone. Where instead at the end of class, you guys are just hand it in and then you leave. And if someone's having trouble, hopefully someone's there to help the last few people, that's all. I'm going to do it at the end. That way you can leave right after you're done. No one has to wait. I'll leave plenty of time. All right, let's talk about the homework you just handed in. First was the written assignment. You were asked to manually calculate the mean, the median, and the mode on the first week's assignment. So, how many pieces of data were there here? Let's see. Is this it? Is this the right assignment? Yeah. Okay. How many pieces of data? 1, 2, 3, 12. 12 pieces of data. When you add them up, I got 705. Anyone else get 705? Yes. Okay, good. Divided by 12, 58.75 is the mean. Median. You had to show me some work, and the work I asked for was showing me that you put the numbers in order from smallest to largest. Don't get me wrong, largest to smallest is acceptable also, but you had to put them in order. That's the big thing. Then you work your way to the middle and figure out where the middle's at. I purposely gave you an even amount of data so that you could show me you remember that extra step you got to take when you have even data compared to odd amount of data. So in this case, there were 12 pieces of data. When you put them in order from 24 to 98, work your way to the middle. The middle is between two numbers, 60 and 61, because of even amount of data. Don't forget, odd amount of data, you just find the center and you're done. You just say, circle it and say, this is it. The median is that number. But because we have an even amount of data, the center's between two numbers. You got to add those two numbers together and divide by 2 to find the mean or average, same word, mean or average, of those two numbers. So in this case, hopefully you added 60 and 61 divided by 2 equals 60.5. Right? Okay, there's that one. Mode. You could have used the same work you did for median. You could have just went up there and started circling numbers that are repeated, but there's only one number being repeated, right? So 65 should have been your mode. And just as far as work, hopefully you had maybe circled it or maybe underlined it or something. I don't even know if I'll take off points for no work or not. I don't know. If a whole bunch of people were showing work and you didn't, yeah, you might lose a point. But you guys got to realize, don't, if you get a 98 on a homework or you get a 97 on an in-class assignment, so what? It's holding your grade up. It's what you got to worry about is that quiz. The quizzes. This homework and in-class assignments, you're all, usually everybody's getting 90s and above for the most part. So it's all about that's holding your grade up in case you fall apart on one of the quizzes, on the test or something. All right, any questions about the manual calculations for these three? These was pretty easy, right? All right, let's go to, I think you also had to do Excel. Here are 3 of them for Excel. This is all about you showing me that you know how to use the correct Excel function that you were taught in class. And the first one was finding the mean of data, and you needed to show me that you knew that the word average. Now somebody emailed me and said that they couldn't find the word average in their Excel. So, you know, listen, I haven't used Excel on a regular basis in years, so I hope they haven't made average disappear, the word average. So did anybody have troubles finding the word average? So it worked for everybody else? Okay, it worked for me, so, but this is an old one, so I don't know, old spreadsheet maybe. Anyway, and then the correct range of the data, C9 through C23, you had to include, did I put letters in here? Let me see.
No, there was no
33, no letters though. Okay, yeah, 33, thank you. C9 to C33, no letters, okay. And there it is, and then you had to write that out, manually write that out, that whole equation, and then give me the answer, which should have been 255.72. Median was showing me that you knew the word to use, the Excel function was MEDIAN, median. Again, parentheses are the same, the range of cells, C9 to C33, and then you tell me you wrote down the answer of 212. And then mode, MODE, C9 to C33s, and then you just had to let me know it was 133. So any questions on using the Excel functions? Everybody knew which functions to use, right? All right, this homework's not bad. You're realizing this, right? That you're gonna be able to keep up with this class. Don't be wrong, it's starting out easy, starting out where homework was less than 45 minutes, but it's gonna build. So we're just starting the momentum a little. We're gonna build. The last problem on your homework was kind of a tailored problem called the number line problem. The reason the number line problem is so important is because it's the beginning of the bell curve, and the bell curve is a major part of statistics. The reason the bell curve is so important is there's a theorem we're going to learn later called the central limit theorem. It's one of the most important parts of statistics that you need to understand. And what the central limit theorem says, that when you have a bunch of data, or let's say it's parts that you have to maybe do quality control, when you have a bunch of things and there's no way you can measure every single part, there's just 10,000 in that box. Instead, you're going to do a sampling. And the central limit rule says as long as you take 30 or more out of that big box of 10,000, you're going to have a pretty fair idea what the average measurement is of all 10,000 based on just those 30 or more. That's the central limit theory. The central limit theory says no matter if those measurements on those parts were exponential, Poisson, uniform, it does not matter. By taking a sample, it forms a bell curve around what could be the average or mean, whatever it is we're measuring, from all 10,000. That's the central limit theory, and that's what makes statistics a big deal. And that's why it's used so much in business, because so many times a sampling has to be done instead of measuring all 10,000. So, central limit theorem. So in this case, this is the beginning of the bell curve. It starts with a number line, and on that number line is always 1 standard deviation above the mean, 2 standard deviations above the mean, 3 standard deviations above the mean, 1 standard deviation below, 2 standard deviations below, 3 standard deviations below. Now I want to correct myself. It's standard deviations right now because we're at the beginning of this class. But we're heading to where all of these numbers are not standard deviations, they're called standard error. Because it matters on what your sample size is. Let me put this equation up here. This is x minus the mean over the standard deviation over the square root of n. This is the number in sample. However many you decide to pick of those parts out of the 10,000, did you pick 30, did you pick 35, did you pick 40, 44, that's that number. But for the beginning of this class, that n is going to be a 1. It's going to be a 1. All the questions to start with are, what's the probability if you were to take one of those parts out of the 10,000, that the mean measurement would be this or that? or that, or this, or less, or more. That's where we're heading. And so the formula, since we know that's a 1, the square root of 1 is 1. The standard deviation divided by 1 is the standard deviation. So at the beginning, we eliminate this part of the formula. And we just have that part. We're only divided by the standard deviation. So to start with, that's 1 standard deviation above, 2 standard deviations above, 3 above. 1 below, 2 below, 3 below. These are standard deviations for right now. But I want you to get in the mindset to know we're heading to where the sample size won't be 1 anymore, and these numbers switch to what's called the standard error because the sample size is larger than 1. Okay, I hope I didn't lose you. Here's the deal. This problem you just did was taking the mean and you were given the standard deviation, and now that you had those numbers, you were able to form the beginning of a bell curve. And the beginning of the bell curve was to add the standard deviation 3 times and subtract it 3 times. And for this first problem, it said the mean was 102 and the standard deviation was 12. So here it is. 102 plus 12 is 114. Plus 12 is 126. Plus 12 is 138. I'll start at 102 and subtract 12 and get to 90. Subtract 12, get to 78. Subtract 12 and get to 66. Now whatever this is, what was it? This is liters. So these were, we were filling, let's pretend this was a manufacturing process, and we're filling up these jugs of whatever it is we're manufacturing. Maybe it's a special compound oil for some giant machines that are all over the United States in manufacturing process. We have these big jugs that are 102 liters on average, up and down maybe plus or minus 12 liters, all right? If we had made 10,000 of these 102 liter jugs of this compound that we're making, that we're selling to other companies, we don't have time to measure all of them. As a matter of fact, we're about to sell a whole truckload of this. But the company that's gonna buy this truckload says, look, we're sending a quality control person over. And we're gonna do a sampling of this truckload of this 102 liter jugs of this compound before we pay for this order, before we have you ship it to us. So they send one of their employees over. And that employee whips out their laptop and takes this thing and hooks it USB on the side, and this thing right here, you're pouring the compound into, and it runs right through it into another jug below that then feeds it right into a jug, so now you just have it from one jug to another's all. But it measures exactly to the 1/1000th of a liter how much ran through it. Because if they're getting shorted, they're expecting it to be 102 liters, and if they're getting shorted, they're not taking this order. This is how it used to be many years ago, exactly like this. And this is why companies said, we can't afford for one of our clients not to take this order after we've made a whole truckload of them. So we need internal quality control using statistics. And that's when companies started saying, okay, we're measuring these before we call the company. We're gonna measure them while the manufacturing is taking place. As the jugs are running off the end of the line and we're making 10,000, 20,000, filling 20,000 jugs of this compound, we're gonna be doing our own sampling. Every time we make 1,000 of them, we're sampling 30. And we're making sure it passed the same test that we know our client's gonna put it through. And it's all based on statistics because they're only grabbing maybe 30 of them or 40 of them. And they're making a decision about all of them just on that sample. So you gotta realize how this all works. And it's all based on this bell curve, right here. And the client says, look, when we measure these, if our samples aren't within, and usually they say 3 standard deviations below or above that 102 liters like we expect it to be, then we're not taking this. But if we do our sampling, and they come and do, by the way, they'll do like 5 or 7 30 jugs. So they'll do 30 jugs, get an average, boom, they mark it. Now they do it again. Let's pick out another random 30 jugs, measure it, mark it. They'll do that about 5 times. And then those 5, all 5 of them have to be between 3 standard deviations above and 3 standard deviations below, or they're not accepting the order. And the manufacturers got to redo all that and make sure they fit to try to resell this back to them as fast as they can, which will cost a ton of money. So some companies will say, we're not taking this order unless we're within 2 standard deviations above or below what we expect those jugs to be. If those jugs are supposed to be 102 liters and we're measuring them and we find the average and we're at whatever the standard error is, if we're at, you know, if we're not within 126 and 78 liters within our averages from those 5 samples, we're not taking this order. Some companies are real particular, and they say, we're not taking the order unless you're within 1 standard deviation. This part's so important, it may be a car part, that if this part isn't within 1 standard deviation, the whole engine isn't working correctly. That's an important part, and that may be, the company may say, we want it. You're a supplier for General Motors, that part's gotta be within 1 standard deviation every time we come to pick up a truckload moving to our sample. That's how it works. So you've got the beginning of this bell curve right here. And you got the numbers, you calculate them. You had another one to do. Let's look at that answer real quick before I go into the empirical rule. And the other one said the mean is 25.2 pounds with a standard deviation of 2.4 pounds. So those numbers turned out to be 25.2 is the mean, 27.6 is 1 above, 30 is a 2 above, 32.4 is 3 above. Now going the other direction, 22.8 is 1 below, 20.4 is 2 below, and 18 is 3 below. So there's the numbers you should have got for that number line. All right. Now I'm coming back to this number line because I wanted to talk about this empirical rule, but before we do that, I want to review these percentages, quartiles, and the interquartile range, and this will be the first time you see the normal range, because I want to make sure you get these, because odds are you're going to be on that first quiz. So let's just go straight to quartiles. There are first quartile, second quartile, third quartile. They are the 25th percentile, the 50th percentile, which is the median, and the 75th percentile. Now, here's the tough part about quartiles. Is a lot of students, when they do their calculations, because you're on a timed quiz, you're trying to stay within a certain time limit, you will do this calculation and then you'll move on to the next problem, forgetting that you just calculated the position of the quartile or percentile. And then you gotta go back and look at the data to figure out what number's in that position, because that's the real answer, not the position. The position is just part of the answer. Now, if I recall, I'm going back to these, let's go back to these rents right here. You have to take the data and you gotta put it from smallest to largest. And then you're gonna be asked a question. Now, forget that calculation there. This is for the 80th percentile, but we'll use it as a guide though, but we're gonna calculate the 75th percentile. So, where am I gonna do this here? Right here? So the 75th percentile would be 0.75 times the number of pieces of data, which we know this is 70 pieces of data. Okay, I need some calculators to help me out here. 7.75 times 70, that's 3/4 of 70, half of it's 35. I'm going with 40 something, help me out. 43? Anybody? 0.75 times 70.
52.5. 52.5.
And then you said the same thing, always want confirmation. 52.5. Now right there, somebody in this room is gonna stop if this question's on a quiz and think that's your answer for the 75th quartile, 75th percentile, which is the 3rd quartile or whatever it is. Because that's not though, that's the position where it's at. Now the rule with percentiles is, if this is 52.0, you're looking at position number 52, position number 53, and then find the mean or average of those two numbers. But this isn't 52.0, this is 52.5. If that's 52.1, if that's 52.001, anything other than just a number with nothing to the right, if you got point anything, you round to the next position. That's it. You go to the next position. So we need to look at the 53rd. And our answer is not that. You still haven't gotten to the answer. This whole calculation is about finding the position. I'm gonna count off the 53rd. 10, 20, 30, 40, 50, 1, 2, 3, 525. So this equals 525. Okay, next, we're gonna do the 25th percentile, which is our first quartile. That's the 3rd quartile. Here, I'll put this right here. 3rd Q. Now we're gonna do the first quartile, which is 0.25 times 70. Someone help me out. 4th of 70 is half of 35, 17.5?
Yeah.
Thank you. 17.5, there we go. Here we are again. if that was just 17.0, we would have to go to the 17th and the 18th position, look at both of those numbers, add them together, divide by 2. But this is the 17 point anything. We have a number to the right. Could be a 1, could be 2, doesn't matter. We go to the next position. So in this case, we're going to the 18th. So we go to the 18th, 10, 20, I know this is 20, so that must be 19. There's 8, right? Am I right? 18? 445 then? 445. Now what's nice about the interquartile range, which is the third quartile minus the first quartile, 5 minus 5 is 0, that'd be 12 minus 4, that's what, 8, 9, 10, 11, 12, 8, 80. $80, because this is rent, so this is how much it would cost for 1 bedroom or whatever small rent, efficiency apartment or something, when we got all these rents. $80 is what's called the interquartile range. Here's what's nice about the interquartile range compared to the range which we're about to learn. The interquartile range takes the numbers on the edges, the ones way up here at 615 and the one way down there at 425, and takes them out of the picture. The reason this is good is because sometimes when you get data, an accident takes place, and you'll have a number that does not make sense. Let's say this number were 1,350. It's so far above any of the other numbers that you gotta say, okay, what's going on here? Was this a mistake? Was there a miscommunication when we had one of our grad students call and ask, hey, what's your rent on your efficiency apartment? And then maybe they thought they said 2 bedroom or something, 1,350. The interquartile range doesn't take that number. That's called an outlier, one that's way off the chart compared to the other ones. It's called an outlier. O-U-T-L-I-E-R, I think that's how I spell it. This is an important term, so I want to make sure you got it. Outlier, or is it AR? AR? It's got to be AR.
No, it's E.
Is it E?
Yes.
Okay, thanks. It takes those out of this consideration. If you have a rent that's so low it doesn't make sense, it would take it out of consideration. This is the range of the numbers you know were probably correct data. Now, full range. Now we're on full range. That is taking the very largest number minus the very smallest number of the data. It's the full range of the data. And it does not eliminate those outliers. So if we had a 1,350, it would be included in this range. Go ahead.
Why did you divide by 80?
Well, I didn't divide by 80. I subtracted and got 80. This is our interquartile range. It's 80, there's $80 between our 525, which is our 75th percentile number off of there, and 445, which is our 25th percentile off of there. And so between them are $80.
Oh, so you're gonna ask us down the quiz to find.
The find the interquartile rate, most likely, possibly, yes. Did everybody hear that? What'd she say? Yeah, I think that's what she said. Isn't that crazy? Okay, you ready? Hang on, what's the full range? Tell me the numbers for my full range. I'm not even gonna look. What minus what? What's the largest one?
615.
615 minus
425.
425? 425, 5 minus 5 is 0, 11, 10, 9, and 1, so $190 is our full range. Look at that, our interquartile range, now that's just purely a coincidence that it's oh no, I thought it was half, that'd be 90, that's not half, what am I thinking? It's much smaller, much smaller. It takes those outliers out, takes the ends, just kind of giving you the range, and when you're comparing 2 sets of data, you have to compare apples to apples. Either you're comparing the full ranges, or you're comparing the interquartile ranges. You can't compare a range of one data with the interquartile of another. You gotta compare apples to apples. Any questions how to calculate a percentile, how to calculate a quartile? Let me again review which quartiles. There they are. The third one and the first quartile, the ones we did. Any questions on how to calculate a quartile or a percentile, or do we feel like we could do this? Everybody, looks like we're shaking heads yes. Okay? All right, we can keep going. Anything? What's next then? We're gonna go to empirical rule, and then we have an in-class assignment, really? Wait, what about life lesson? What about my drive? Here we go. New record. I forgot to look at when because I refused to shovel. Does anybody else have any shovel? Anybody shovel? You guys shovel. Yeah, it just seems like a waste of time. You can just drive right over it. We got cars out here, just go right over it. You don't need a shovel. Anyway, I forgot to look at my clock, cause I thought it was gonna get stuck, cause I didn't show. But it ended up being 110, over 110 minutes. I don't know the exact time, but I know it was over 110 minutes. That's a new record. Don't forget, my shortest time is 59 minutes. So you can see a 59-minute drive turned into over 110 because of the weather. So one major accident and two minors, but the major one was major. The car looked like it. Totally, the whole front end was completely bashed in. All right, let's get to the empirical rule. Wait, what else? Oh, Nielsen. Okay, here we go. What do you think about this? Have you guys ever watched, you're watching your TV shows? You know, it could be a Netflix show, it could be a regular NBC, ABC, CBS show. And you hear, I know the Emmy Awards were on recently, I don't know if that was last night or the night before, but you hear a lot of things, TV shows are all about, okay, how many people watched us last night? How many viewers did we have? And that's kind of what determines how much advertising will cost for those who want to put advertising on shows. It determines if a show will continue through another season, or even if a show makes it through the season they're in. And I always wondered, hey, you know, have you ever thought about how do they know how many viewers they have? It doesn't even make sense. How could they tell? There's nothing on our TVs giving them information as to what we're watching. Well, I don't know if anybody else in here has ever been a Nielsen viewer rating sample. Have you ever been chosen as a sample for Nielsen? Nobody in here? Raise your hand. Seriously? Well, you will, because I've been chosen 3 times already, but I'm an old man, so you can just give it some time. And what happens is they contact you with a letter telling you, asking you if you would be willing to do this, and then you get online, you say yes, and then they ship you this booklet. And in this booklet, here's the weird part, and by the way, they're gonna pay you, but it's not much, but they're gonna give you money for helping. But in this booklet is like every single day, and the time intervals are 15 minutes apart. So every 15 minutes that you're watching TV, they want you to write down what you watch. So if you flip the channel and you're watching something else, 15 minutes later, they want you to report what it is you watched every 15 minutes. So if you watched a show for an hour, you're putting the name of the show in the booklet, and you're just drawing a line for all the way down a whole hour. So it's obvious the same show for a whole hour. And in the old days, you'd have to mail that booklet in, and then they send you like $10 or some crazy amount of money. But I think now, the last one I did, I went online and transferred the information from the booklet online, I believe. So it's that booklet that we're all putting online the next day after we watch TV. And by the way, you do it for a whole week. You get chosen. You have to fill it out for 7 days as to exactly what you watched every single day. And they're getting a sample of maybe a couple hundred every day. Maybe a couple hundred people every day is determining what everyone's watching. But now there's such a selection of shows, they have to keep increasing their sample size. Because back in the old days, when I first got chosen for Nielsen ratings, there was only 3 networks, ABC, CBS, and NBC. There was no such thing as Netflix. Internet wasn't even invented yet. There wasn't even a Fox. There wasn't even a 4th network yet. And so, you know, there was public TV, and then these 3 major networks, and that's all the channels you had. And so it was, you know, it was pretty easy with maybe just 100 people to tell us that they would literally say this sample now is going to represent millions of people who watched TV the night before, so we know how many people watched it. But now the sample size may be 1,000. But they're basing how many people watched every show every night based on those 1,000 people that are randomly selected, that are agreed to go ahead and fill out that booklet and enter the data in. That's how it works. It's statistics. And they're taking the statistics and applying what you're learning in this class to determine then, okay, if there's this many out of 1,000, that means this many out of millions. And that's how they do it. So that's how Nielsen ratings work. You guys, you at least heard the word Nielsen ratings, have you? Anybody raise your hand if you heard of Nielsen ratings? Well, those Nielsen numbers are exactly what they're always talking about when they're saying how many people watch this show, how many people watch it. Go ahead.
You can actually volunteer to do it as well.
You can volunteer to what?
You can volunteer to be a panelist.
Oh, really? To do the Nielsen thing?
Yeah.
Yeah, I didn't know that, but do it. It's not that bad. I mean, if you're willing to fill it out. I want to tell you, back in the old days when there's only 3 networks in public TV, I used to change channels so often that it was like, wow, I can't remember what I watched those 15 minutes because I was changing channels so much. I had to I'd kind of like fill in my favorite show. I go, well, this is the one I really liked that 15 minutes, so I'll put that one in. Even though every commercial, I'm switching to another show, because they're all so boring. Anyway, let's get to the empirical rule, then our in-class assignment. We'll get out of here. Whoop, whoop, whoop. Here it is. There's the drawing. There's a bell curve. That bell curve's a lot better than mine. If it says that if you have 10,000 of these, whatever these are, and you know the mean and you know the standard deviation, then picking one of them out of there, there is a 68.2% chance that the one you just picked out will have a measurement within one standard deviation of the mean. If you know the mean and the standard deviation of these 10,000 parts here, whatever it is we're measuring, and you randomly pick one out, that measurement of that part will fall, the probability of it falling between two standard deviations above and below are 95.44%. That's a high percent chance that the one I just picked out is within two standard deviations of the mean. And then if you want to go 3 standard deviations, okay, I just picked out another part. The probability of that part's measurement being within 3 standard deviations above and below are 99.72%. That's a huge percent chance. Okay, now that we got that figured out, there we go. What you now have is enough information, that's not what I want, this is what I want. Enough information, right there's the drawing, to be able to take this now, I'm gonna draw my sloppy, awful bell curve here. Hang on, I gotta start down here. And then I know to go up and then bell it out, bell, like that. Okay, let's try it down here. Go up, and bell it out, and it's awful. Hang on, let me go there. Okay, there's that. So between one standard deviation above and below is 68.26. So that means from here to here, right here, boom, boom, 68.26%. 0.6826 or 68.26%, right there. Now, I need you to start thinking algebra. You gotta use logic, algebra, basic calculations to answer questions like this. If I said to you, hey, what's the probability of us picking a part out that the measurement of that part is between 102 and 90? Estimate the probability that we are going to take that part out, and the probability of that part being between 102 and 90. Oh, these were the liters of chemical, was it? Okay, we're picking one of the jugs of chemical out, and we just measured it, and the probability that the amount of liquid in that jug was between 102 and 90 liters. What's the probability? Estimated. There you go. And what you just did, you said, well, all the way between these is 68.26. Half of that would be from 102 to 90. So you took 68.26, you divided by 2, and you got, let me look here, 34.13?
Yes.
34.13% is just one of these right here. 34 point, whoop, come on. Hang on. I'll make this good. 13. Okay, now, let's take this farther. We're going 2 standard deviations now. We're going 2, all the way from here, all the way to there. Let me put this arrow here. Let me go all the way to there. And this one is 95.44. Where should I put this one? Right here. 95.44%. Okay, so if I said to you, hey, we have all these jugs here, 10,000 of them, we're about to pull one out, what's the probability that we just measured the amount of liquid in that jug, what's the probability the amount is between 102 liters and 78 liters? Now, look what I did. I asked you about what's the probability that jug will have between 102 and 78 liters of liquid in it. Right there.
47 point.
Half of the 95, very good. 95.44 divided by 2 equals 47.72%. Right there. So I'm going to do just over here. I'm going to do from here, just to there. Just half of this 95 is 47.72. Okay, hang on, we're almost there. I wanna stare at this for a second. I forgot to tell you something. Underneath this bell curve, by the way, this is all about that area under the bell curve. From the number line to the top of the bell curve, it's all about this area. This area, and by the way, look, that end is open. We aren't touching the line there. We're not touching the line there. There's always that little bit way out there, that teeny, teeny little bit out there. So we're not all the way to the line. But that area all adds up to 100%. It all adds up to 100%. And between 3 standard deviations above and below is 99.72%. So that means outside of that 3 and outside of that 3, that little spaces on the end would be the opposite of the 99.72. So what I'm trying to get at is once you know what the amount of amount of 100% that's underneath each one of these locations, from -3 below, from -2 to -3, from -1 to -2, from the mean to -1, from the mean to +1, from the +1 and +2, from +2 to +3, and from +3 to that little end there. Once you know each of these, you can answer then any statistical question, such as, what's the probability we randomly pick a jug out of the 10,000 there, we measure the amount of liquid that's in it, and it happens to be 114 liters or less. 114 liters or less, you've got to use algebra. If we had done this whole thing, you would be able to say, okay, that's right here. You would add that one plus that one. Well, we know these two are 68.26, so we got those. Then you would add that to it, and that to it. For 114 or less would be all of those added together. So you're getting it. Now here's the deal. No matter, when we did the first number line and we did the second number line, they were completely different numbers. Well, I didn't put the other numbers up there, but they're completely different numbers. But the concept I'm teaching you, once you know what the number belongs at +1, +2, +3, -1, -2, -3, once you know those numbers, you can calculate any probability about those numbers. The bell curve is the same, it's just different numbers on the line. That's all it is. Once you know that standard deviation. Okay, now I want to make sure I got this. I want to make sure I got this. We now need to relate this to a Z-chart. Right? Because the Z-chart is doing what we're doing for us. You ready? I said to you, what's the probability of 114 or less? All right, and we know, look at this. Oh no, we don't know. I was gonna say, we know the middle one is 68.26. We would have had to add this one, and we would add that one and that one to it. But what we do know is that 114 is right there at the +1. Right there at the +1. So we have a Z-chart that will tell us right there at that +1 what the amount of bell curve there is from there to the left. The Z-chart tells you from any number on this number line, it converts it to either a +1, +2, +3, or any of those numbers between it, and converts it to how much of that bell curve there is from that spot to the left. So let's look. Are you ready? Hang on, where is it? Boom. Here it is. There's the bell curve. It will tell us, if let's say we want to be a Z. Now, here's how we look at this. This Z is the first number to the left of the decimal and the first number to the right of the decimal. At the top is the second number to the right of the decimal. So if I said 0, let me put one on the board. I want to make sure everybody's with me. If I said 0.12, on the left, right here where my pointer's at, is 0.1, then the 2 would be over here, underneath this 2. So the probability for that would be 0.5478. Now, hang on a minute. I know I'm going a little too fast. I want to make sure you understand what I did. I'm showing you how to read this Z-chart. So if I said Z equals 0.12, you would go to the 0.1 column and then go over to the column that has the 2. The columns to the right are always that second digit. The left-hand column is the first digit on each side of that decimal. Here's the thing we're talking about though. We're talking about 114 or less, which is at 1.0. 1.00. That's where 114 lands, right there. So if we went here for 1.00, let me scroll down. Right there it is. There's 1.0. There is the second 0. I now know that the amount of bell curve from 114 to the left is 0.84? 8413. You ready? I'm putting it all together now. We have 10,000 jugs of that liquid in there. They're supposed to be around 102 liters, right? Each, approximately. And I said to you, I want you to go pick a jug out of there, and I want you to tell me what's the probability that you're about to measure that liquid, and it's 114 liters or less. That answer is an 84% chance, a little over an 84% chance. 0.8413 is 84.13% chance. We can answer any of these questions because now we know the mean, we know the standard deviation, we can answer any of these, and look how fast we can look it up. You ready? You ready? What's the probability that we're picking one out of the 10,000 and it's 90 liters or less? 90, what should I look up on the Z-chart?
-1.
-1.0, because 90 lands right there at the -1 on the nose. So here's the deal. This part of the Z-chart is for all those numbers to the right of 0. They're all positive. And by the way, from the mean to the left is 50%. From the mean to the right is 50%. I almost forgot to tell you that rule. 50% is each half. Whoop. Each half is 50%. So there's another number that's known that will help you get these calculations if you didn't have a Z-chart. Now, if we don't have a Z-chart and we're using the empirical rule, and I just asked about 90 or less, you go, oh, if we know the probability from that -1 to the left to that 2, if we know that little bit, or look at this, you know, you could use algebra to calculate what that probability would be based on the empirical rule. You could say, look, here's 34.13. I know it's 50% from the mean over. If I subtract that 34.13, that what's left is from that -1 over. So 50% minus 34, here we go. 50 minus 34.13. That's gotta be, what is that, 15.87 maybe? No, is it? Percent?
15.87.
15.87%. We just used the empirical rule to figure out. So I'm gonna put it all together now, you ready? Hey, go pick out a jug out of those 10,000. Pour it into the machine over here to measure exactly how many liters. What's the chances that that one you just picked out is gonna have 90 liters or less? 15.87% chance. Let's use the Z-chart and see if we're right. This part of the Z-chart's only if we had a number above the mean. This number is below the mean, so we have to go to the negative part of the Z-chart. Let's go to the negative. Hang on, almost there. There, let me go up here. Here's the negative part. All the numbers are negative. This is -1, -1.00. So we gotta go to the -1.0 and then over to the 0. So let me get to the -1.0. Here we go, right there. And then the first column is the second 0. And look at that, 0.1587. I'm gonna stop there because that's a miracle. You're getting the hang of it. This is just an introduction. It's just getting you used to it. This bell curve is the fundamental basis of statistics, the central limit theorem, the empirical rule. You're gonna have problems all semester where you're given like the mean and the standard deviation, and you're gonna be asked questions. What's the probability of 126 or less? What's the probability of 138 or more? What's the probability of 114 or more? And you're gonna be able to go boom, 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 Z-chart it. And then we're eventually by week, I can't remember, 5, I think, 4, we're gonna stop using the Z-chart. And we're only using Excel to calculate that probability from that point on. But these are the fundamentals. You ready for last week's in class? I'm gonna give you a hint. Wait, that's it, right? Any questions? I'm sorry. Any questions about the empirical? Go ahead.
Are we gonna use this thing? We're gonna have this thing.
Yeah, the Z-chart during the quiz?
Yeah.
Absolutely. I posted on anything posted on Canvas that you should have ready to go as a tool while you're taking the quiz. And this Z-chart is posted in week 2 module. Yeah.
The empirical rule is always those 3 percentages, right?
Always these percentages. 68.26, 95.44, and 99.72. Yep. Only thing that changes is these numbers on the number line. Yes?
I didn't catch what you said what an outlier was.
An outlier, if we had data where the number doesn't make sense, it's like, remember all those rents went from 600 and, where's that at? Where's our, 615 to 425? If we had one that was 1,300, it's so far above all the rest of the data, it doesn't make sense, that's called an outlier.
Oh, okay. Wait, is that found by the range?
No, it's found by, when you finally put the data from smallest to largest, you'll see this piece of data doesn't even fit with the rest of the data. But you're allowed to find what's called an interquartile range. It doesn't, it takes the outliers out of the picture because it's only using the center 50% of the data. Any other questions? All right, now I'm gonna give you a hint about the in-class assignment we're about to do. If you remember from last week, one of the key things I taught were how to make a frequency table, a relative frequency table, and a percent frequency table. Remember those three? All right, here is your in-class. How much time we got? We got about, plenty of time. Has to be, well, I don't know. I don't know if you know how to use that printer, I guess you could print it. I don't know. Oh, you can email it to me. Is that what you're saying? But how are you gonna compare it to everyone? How do you compare it? Okay. All right, here it is. Give the relative frequency for each day. Show your detailed calculations. Let me emphasize that. You gotta show me how you got each one of those relative frequencies. Use at least 4 digits to the right of the decimal for rounding if you're gonna round at all. You can go more than 4 digits, but don't go less than 4 digits. Unless the 4th digit's a 0, you know, you can go 3 digits then, but you know what I mean. All right, good luck. Did I make it big enough? Or make it bigger? There. Now we have another in class on Thursday, don't forget that.